Hello everyone, this is Team 3 and we'll be presenting our project on camera model identification using neural nets. For this project, we followed the flow as follows. The first step was to perform exploratory data analysis. So what we did was the initial step was to find out if there is any class imbalance in the dataset, whether the dataset is favoring any device and which would lead to a skewed model. So we checked that and we found out that that was not the case, which is a good point. Later on, we checked upon image size distribution in which we explored the pixel width and that height and width for each image. Then we did some RGB channel distribution in which we calculated the standard deviation and mean of images per device. And the last one was image count distribution in which we found out that we had equal number of images for each device in the training set. So moving on, we moved to augmentation. For data augmentation, we did horizontal flipping, center cropping, resizing, and random rotations. For training, we tried various different baseline models like Various 16, Inception V3, TenseNet, and we found out that TenseNet has a better overall performance. So we use transfer learning by unfreezing the classifying layers, and we use the Adam optimizer along with cross entropy categorical loss functions. Lastly, moving on to validations, we had split the dataset into a 70-15-15 split, and hence which resulted in a baseline accuracy of 49%, and our particular model gave an accuracy of 63%. So the motivation behind this challenge was to address the challenges of image forgery with advanced techniques. This basically helps in forensic analysis, and this project explores the use of TenseNet to identify unique camera features or fingerprints. The task was to improve the accuracy of a prediction of the baseline model, and we did this using the TenseNet model. The dataset consists of folder structure in which we have 10 different folders and each folder has 275 images per device, and the test dataset also has a similar structure in which we have the images from the same 10 devices but same 10 camera models but a different device. Here are some of the sample images. The first model we chose was GTG16, in which is a 16-layered convolutional neural network which contains convolutional layers, max pooling layers, and fully connected layers. This is the architecture of GTG16. Here are some of the baseline results that we got, in which you can see the true label and the predicted layer. But to our surprise, VGJ16 only gave us an accuracy of 49%, and we moved on to explore DenseNet. So for DenseNet is a neural network in which every layer receives input from the preceding layers, and it uses feature usability. So the features benefits are like parameter efficiency. It has fewer parameters than traditional CNN. As I said, it uses the features that have been explored in the previous layer. So this is the DenseNet architecture. The improvised model, as I said, DenseNet has a better parameter efficiency, so it results in a faster training. The gradient flow is also better. VGC16 has a sequential nature, so gradients get vanished while propagation. Feature reusing is used in DenseNet, so the features on the previous layers and also the input from the previous layers is propagated to the next layers, which helps in better training of the model. Finally, for comparing our results, we found out that the baseline that we used was had a test accuracy of 49% and an F1 score of 47. But our proposed our model using DenseNet, which we as a base, and we use some techniques to transfer learn with our dataset had an accuracy of 63%. The F1 score was 61. So these are some of the sample results from our improved model. This you can see the true label, predicted label, and the image in the slide currently being shown, and it gave us pretty good results. It has a considerable accuracy. So concluding the PPT, we achieved a 14% improvement over the baseline, which shows that our model has promising results. We believe that we can further improve this by fine tuning the training process, specifically by unfreezing more of the layers, which will result in a better model and an improvement in the accuracy as well. Thank you.